Thank you for your patience. And again, my name is Ryan Morris, and we will be discussing the value of machine vision and going into the different technology types with 2D versus 3D machine vision. We will be talking about the structured light approach, stereoscopic, time of flight, laser triangulation, and then going into some successful applications as well as an emulator demo of our 3D tri-spectre product. So getting into this here. So vision. So vision is kind of, it's a technology that is getting more and more prevalent in the industry. Typically in the past, you usually used multiple sensors when you needed to do an application for determining the presence or absence of product, positioning applications. And typically that, gets you to a point where you are really kind of pinpointed into where exactly you can see. In reality, typically parts will move around and can't be positioned properly, and that causes a lot of errors where vision can solve where typical photoelectric sensors may have fallen short. Other applications include part color consistency changes, as well as, as well as positioning. So as part colors change, as positioning change, that can make applications very difficult, especially if you're utilizing standard photoelectric sensors. So where is a product can be solved with vision. Is a product or a package okay? So content verification, is all the parts and pieces exactly where I expect to see them? How large? Start doing distance measurement applications, as far as, width measurements, hole diameters, making sure that the threads are positioned correctly. And as well as what does it say? So typical image-based code read applications where you're starting to read 1D or 2D codes that may not be positioned correctly or may float around a package. Vision provides the flexibility to be able to read those codes and find those codes as it moves around in the field of view. So typically with any of those combination of tasks, that's where a vision solution really comes into play. A lot of multitasking capabilities. Not having a standard sensor just for doing one item or one task. Vision is able to do multitasking and be able to do all these in conjunction with one another. The different technologies that we will discuss here range from 2D image processing, which is standard 2D image vision. How that works is it's just like your iPhone or your whatever camera you might have. It's a 2D snapshot image of a object to be inspected, and it acquires that area image. Internally inside the camera, it will do some of the analysis based on color or contrast-based inspections. So you're really looking into transitions between light and dark pixels to really do your inspections. Some of the downfalls to this is obviously there is external ambient illumination conditions that really can come into play to really give you a reliable inspection. With the ambient conditions changing, you might start to lose some contrast that you're looking to see, or you might have some hot spots that are affecting the acquired image to be very repeatable. There are some methods as far as shrouding out or external illumination options to make sure that you can get a consistent image. But there are scenarios where just a low contrast, black on black, white on white are very, very difficult applications for a 2D vision application. With 3D kind of provides a little more flexibility as far as being able to counteract those scenarios where you might have some low contrast scenarios, or you might have lighting issues that you're not able to shroud out. 3D vision typically uses an internal light source that it relies on instead of using the ambient conditions. So again, low contrast scenarios, scenarios where lighting might be an issue. Anything where height information can be valuable really kind of plays into the fact where 3D vision really shines. We do create a 3D height map or pixel point cloud of the image, so any kind of small deviation in heights are really able to be detected with 3D vision more reliably, whereas a 2D solution might falter in that scenario. All right, a little lag on my side here. All right, so the main 3D vision technology types, so we'll discuss here right now. There are a few different technologies that are incorporated into the 3D vision. There is a standard structured light approach where you're projecting a structured light onto an object with an external 2D camera actually recording and analyzing the different height variations that that structured light projects onto an object. SICK does not really have an offering in the structured light portfolio as of today, but it is a standard 3D vision technology that is out there. Stereoscopic. So this kind of looks like how your eyes would work in a 3D space. Typically, there's two images being recorded by two different cameras at two different angles, and a 3D detection area is generated based off of the feedback from those two different cameras from the two different angles. SICK does have an offering with the stereoscopic vision, more so for large spaces or room detection. So you're looking for objects in a room or a palette, obstacle avoidance. So more so in those type of applications. Time of flight laser array. So this is similar to the stereoscopic approach, except we are actually blasting a bunch of different laser lines or different photoelectric beams out into a field and recording all those feedback as those distance measurements come back to create a 3D space or 3D view of the entire space. Again, more so for larger rooms, looking for obstacle avoidance again, content verification of packages on a pallet, applications where you might have a need for a wider view of a room. And then we really dive into our laser triangulation devices. So this is probably typically the most common 3D approach out in the market as far as projecting a laser line down onto an object as it moves underneath that laser line. We record those different laser profiles as that object moves through to get a high resolution image of a 3D object. And we will spend the majority of our time today talking about laser triangulation. So how triangulation works. So there is 1D triangulation, is how a typical distance measurement sensor may work as far as a triangulation distance measurement sensor, where you have a single point that is projected onto an object. And as that object moves further and closer away, that 1D point on the sensor receiver is actually determined to give you a distance measurement. 2D triangulation works on the same principle, except it is no longer a point laser, but a fanned out laser line that is projected across the entire object. And as that object, again, moves closer and further away, the 2D receiver records those profiles and gives you a position as far as how far away that object is. And a height profile is determined. 3D builds on this 2D triangulation principle, except now we are adding in the dimension of motion. So as an object moves through that 2D laser line, we are recording a bunch of different profiles as it is passing through that laser line through the determined field of view as it travels. And that's where we get our 3D evaluation. So you really kind of think of it as a loaf of bread. So we are recording a bunch of slices of bread and creating our loaf as that object moves through the 2D laser line. So we got a nice little graphic here as far as projecting that laser line. The camera is recording each individual profile, and there is a filter inside that camera that is specifically looking for that wavelength of laser. So again, this is where that ambient condition scenario really kind of falls apart as far as not really relying on needing ambient lighting conditions or ambient conditions in the environment. So as I'm recording that red wavelength of laser, any other colors in the spectrum I'm ignoring out and not really seeing because I have a filter inside the camera that is only looking for that red wavelength. So again, as those objects moves through, the camera is recording those individual height profiles to create our 3D image of those collection of different height profiles. Typically, in a triangulation setup, you do require the motion. as an object moves underneath the camera or as the camera moves over an object. We trigger the device with a photoelectric sensor or an Ethernet command or an object trigger as soon as I see a first profile. And then as that object passes through, an encoder pulse or a free running scenario records those image or those collection of profiles at a nice equal distance from each other. So if I have a 1 millimeter profile, I'm going to take a 1 millimeter slice of bread every single time that that encoder pulses. So getting to the field of view. So this is where we get a little different as far as when you start to compare a 3D field of view and a 2D field of view. So as that field of view, as you can see here, is the intersection line between the camera sight line and the laser line. A typical 2D camera is going to give you your nice square or rectangular field of view that the camera is actually seeing. 3D triangulation is really going to give you more of a trapezoidal shape, where that intersection line is between the camera sight and the laser line. So anywhere above or below that camera sight line is pretty much not recognized by a 3D triangulation device. So that maximum field of view then is where that intersection point happens. There are some benefits to utilizing 3D vision as far as being able to really identify exactly where in your field of view you want to analyze. There's no real reason to analyze the entire maximum field of view when you're, say, inspecting a bottle cap on a pop or soda can. If I'm looking for that bottle cap to make sure that it's present, that it's not cocked or not tightened down all the way, I don't care about the rest of the bottle. So what I can do here is you can actually select your field of view down to just the region of interest that you really care about. There are some benefits to you doing this, obviously selecting down a field of view. One of the main reasons is data reduction. You're not processing information that you don't really care about. So reducing down that amount of data will really increase the speed that you can actually achieve with a triangulation device. Another way to increase your speed is actually where in that field of view I'm selecting that field of view. How this green box is selected right now, it's in the bottom end of its camera sight line. And with the geometry of the sensor chip itself, you actually have a little less resolution in the Z height near the bottom than you would near the top of that field of view. So you have your near field and far field resolutions. There's a little chart down in the left corner there. As you can see, obviously there's different resolutions in the height as far as near field versus far field. Again, by reducing this field of view down to the lower end of the field of view, you can also increase speed because it is less data reduction. So you will be having less resolute images, but you can get increased speed by that, by selecting down a field of view that is nearer to the lower end of the resolution range. In contrast, if I were to have that up at the top, I get a lot higher resolution, but you might decrease the capabilities of what speed you can actually require because you are processing more information there. All right. There are a couple drawbacks to 3D triangulation that 2D might not have. And that's a phenomenon that's called camera occlusion or shadowing or laser occlusion or missing data. So basically what that is, since the camera is looking to record that laser line, if the laser line is not highlighting a part, let's say on the sides of a part, you might get some laser occlusion, so you'll get some missing data there. Whereas if behind a pillar, if the camera can't see it, I'm going to get a shadow on that pillar is going to create a shadow, and I'm going to have some missing data behind that little pillar in the bottom right corner. This is kind of a phenomenon that's going to happen with any kind of triangulation device. There are a couple of options as far as helping avoid camera occlusion, and that'd be the addition of multiple cameras or possibly tilting a camera or reorienting a camera just to get to the point where you're actually looking and inspecting the area of interest that you really care about. If I'm not doing any inspection behind that pillar, maybe that's not an issue. But if I'm looking to make sure that that pillar is there or that pillar is at the right height, camera occlusion really doesn't affect how the image is being processed or the inspection to be done. So it is kind of a an art form as far as where exactly you want to position the camera and what you actually want to inspect. As far as when to utilize 2D or 3D sensors, 2D obviously has a lot of benefits as far as being able to do nice inspections based off of contrast, but as soon as you start introducing height information to it, 3D really kind of shines. In this robot picking application, you can see with a 2D view versus a 3D view, 2D is basing its inspection on that transition between light and dark. So it's really, the camera itself cannot determine which part is on top, especially for a robot picking application here. Whereas 3D, since I am doing a scan and I get some height information off this, I know exactly which part is on top, and it makes a 3D robot picking application much more reliably done when you utilize 3D versus 2D in this type of scenario. Again, low contrast scenarios again. So looking for the presence of a gasket. Looking straight down on this, this might be very difficult in a 2D application to determine if that gasket is actually present. Again, since 2D is really utilizing contrast-based inspections, if I have a black part and a black gasket, there's no contrast change between a light and a dark transition. You might be having to introduce a lot more external lighting than you typically would have to do if you're looking for a gasket or a low contrast scenario. Whereas 3D with a simple scan, you're able to get that height information if the gasket's there or not there. So you really get that correct positioning and presence of that gasket. So again, another one of the value adds to a 3D inspection when you start having the introduction of a low contrast scenario. Again, another packaging application here as far as when and when not to use 2D versus 3D. So here's a package of chocolates that you as you can see here. Again, another scenario where we have a very low contrast package here where you're trying to decipher between the packaging itself and whether or not there is actually content or a chocolate in the respective slots. From a 2D view down looking, you can kind of see there are shapes and contrast changes in the areas that actually do not have chocolate. And it'd be a very, very, very difficult application to try to solve with a standard grayscale 2D solution. Again, with 3D, looking with that height information, I'm able to determine exactly that there are blobs or pixels, height pixels, in each of those regions that I'm expecting to see an object or a chocolate in that image. So again, as I talked about multitasking earlier, this is another one of those scenarios where multitasking really comes into play. You could have a dozen different photo eyes looking straight down on this box of chocolates, making sure that there's a presence in each one of those slots. Whereas 3D, since I can just take a quick scan, I can determine presence. Is a chocolate there? But then I can also start doing counts as well. So I can say, okay, a chocolate's there, and do I have the right amount of chocolate? If I'm expecting to see 20 pieces, are there 20 pieces there? I'm really able to determine that. What are the areas of those chocolates? I can also put what's the surface area? What's the volume of each of those chocolates? So you're able to get a lot more multitasking done with a single 3D image, whereas 2D might be able to do a count and maybe be able to determine if something's there or not. 3D really kind of shines where you're able to do a lot more multitasking based on height information. All right. And again, some consumer goods part identification reading applications. So we do have a portfolio of products that can also actually do OCR and code reading applications. Again, you can kind of see here, again, lighting, low contrast scenario with a 2D view, really trying to identify to make sure that embossed A is in the part. With 3D view, again, you see a little bit of the occlusion or shadowing, that might happen around the rim of the center of that part. However, able to get the majority of the part that you really care about seeing and gain that height information that A is present. And then vice versa, being able to actually identify, is it an A, is it a B, is it the correct embossed feature that I am looking for. So it makes identification much easier when you're able to utilize some of that 3D height information. So a few more application examples where 3D really kind of shines. So we have some real world scenarios here as far as different inspections that are being done. So again, this really kind of gets into some more of that tougher 2D or being able to get more data out of a single scan of a 3D solution where a typical 2D or photoelectric sensor might have some of those limitations. So here's a capping example, which you see quite often in the field as far as, is the cap present? Is the cap tightened down all the way to the correct height? Is the cap skewed? So this one, we actually utilize just a few different tools, a couple of plane tools, finding the surface plane of the milk carton, finding the surface plane of the cap, doing a simple distance measurement between those two planes, and does it fall within the threshold that I'm actually looking for. And then as far as the cap plane, I'm also able to output a tilt value. So is the cap actually skewed at the right angle, or is it not tightened down or skewed in the improper orientation? Also able to do just, is there a cap present there or not? So a lot of typical applications that you might see with just a cap inspection that is really simply done with one scan, being able to multitask and do a 3 or 4 different inspections right on the fly there. Wrap seal detections. This might, again, a little candy bar wrapper that you might see looking for, is the wrap sealed? Typical 2D view might be very, very difficult to try to decipher if that cap or that wrap seal has been sealed on the both ends. With a simple area tool, making sure that I scan the image and is the area sufficient enough where a unsealed wrapper would produce a lot more area within an inspection region. Whereas if it is sealed, it's going to give you less area that I know that that seal is wrapped, or that wrapper is wrapped and sealed correctly. So another simple application that might be very, very difficult for a 2D application where 3D triangulation really shines. And then I mentioned a lot of counting applications. So you can see a box full of different vials. Could be mix and match different colors where, again, 2D might be really, really difficult, especially if a mixture of colors, because it's always going to give a lot of different variations in contrast, where 3D doesn't really care about color whatsoever anymore, does a quick scan and is able to decipher all those different heights since there are separation and give us an accurate count as far as, are all the caps present, are all the caps the correct area. Simple scan that might take a very, very long amount of time to do with multiple 2D cameras or multiple photoelectrics, where a 3D scan really kind of gives you that high-res capability to be able to do massive counts in a single scan. Again, color independence is really kind of where 3D shines. We're not really relying on contrast-based inspections. All I really care about is that the height information is there and a count is achievable. A couple more automotive examples that we have here. Again, these could be packaging applications as well. It doesn't necessarily have to be an automotive scenario, but making sure that there is a part present in every bin that I'm expecting to see a part. So doing counts applications, completeness checks, being able to send part positioning as well. If this is going into a bin picking or a robot picking application where I want to know the centroid of that part to pick, I need to know the orientation of that part, and is that part actually present or not. So another ease of use scenario where being able to triangulate all the different information, all the different height pixel information in each of those carriers to be able to determine that the part's present. I get the X, Y, Z rotational information for a pick application. Makes it a very simple application utilizing 3D. Assembly control, again, this is the same, doesn't necessarily have to be automotive here again, but looking for part presence verification. Are the bolts or screws properly positioned? Are they in the right position? Are they present? Are they orientated correctly? So another assembly control application where this could be electronics, looking for IC chips or resistors or transistors that might be present. So able to do assembly control and make sure that the parts are present where they need to be. and in the correct position. And orientation. So again, orientation really comes into play with a lot of pick-and-place applications where you need to find and identify a part. I need to know the X, Y, Z, and I need to know rotation information. So with that, able to identify a 2D view would be very difficult to give orientation based off of these tabs that you can see highlighted in the red boxes there. A 2D view really can't determine if those are tabs or if they're just little wings that are part of the part. With 3D, I'm able to identify those tabs and give a proper orientation for a pick application when I need to know exactly where I need to pick this part based off of the height information of a tab. So again, low contrast scenarios where 3D vision utilizing that height information to be able to determine exactly what the orientation of a part is. So kind of diving into an emulator view here, and I'm going to try to switch programs here, just kind of show the capabilities of our of what a 3D vision application might look like. I'll give it a couple seconds here and make sure that this is loaded up. So here is an application looking for a count of tea bags in a tea box. And Lisa, I know we had issues with this the other day. Is this showed up on your screen right now?
Yeah, it looks great.
Okay, perfect. I'll try to go through this a little slow because I know there's a little lag that it looks like that we had previously. So, so this is SOPAs, which is 6 configuration software ranging from anywhere from ultrasonic sensors all the way through our 3D vision camera here, our Trispector 1008 in this case. So traditional 2D view, again, this could be various colors of tea bags. It could be a low contrast scenario. It looks pretty nice with the 3D view. However, this could be a very difficult application for 2D, especially if there's low contrast or color variations among those tea bags. So as we look here from 2D view, we can kind of rotate through and we actually see that height information that we get out of a 3D camera. As I mentioned before, there's your trapezoid field of view, and the blue box is actually your selected field of view. So in a scenario like this, we can actually, again, reduce down that field of view to the region of that I actually care about. Again, this is reducing down that amount of data that I'm actually processing, and really just inspecting that blue box and not really inspecting the rest of that green area, since again, not something that I really care to inspect. But you get a nice little 3D view, and you actually get some intensity information here, so I can actually make sure that open here or that intensity information is exactly what I want to see there. So not only am I getting 3D height information, but I also do get intensity data back via the Trispector with the intensity view. So as we go and move into a task, we have our nice sample image here, and we can just save that job image. As we save this job image, now we start to get the tool sets that we have available to us to be able to perform our inspections. From a shape tool, again, objects might move around in a field of view, so a shape tool would actually kind of find and locate that part as it travels or moves around a field of view. And then subsequent to that shape, I will tie all my additional tools to that shape. So as that shape moves around, all my subsequent tools will be tied and pinned to that shape. So we have blob tools, very similar to a 2D blob tool where you're looking for clusters of pixels in a 2D grayscale. 3D, same type of scenario, except instead of looking for clusters of pixels in a 2D contrast-based, I'm looking for clusters of pixels based on a height range. So you see as I add in that blob tool, it's looking for pixels that are all clustered together. It gives you an output of all those different blobs that are inside of that 3D view. So as far as performing an inspection, again, I can reduce down my field of view. I'm trying to do a count here to make sure that they're all properly counted inside of that T box. And as I get this, I can again reduce or make sure that I catch all these T bags, and I can get a nice count down here that I'm looking for 19 blobs, and I found 19. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we got all 19 there. So that looks good. As you can see here as well, if we go down into our array of information a blob tool can output, it gives the area of each one of those blobs. So looks like ranging from 193 to about 104 based on the clusters of pixels in that area region I'm looking for. And here I can actually define exactly what is a blob. So say there is some miscellaneous noise that might pop in there and all of a sudden I see 20 and I'm expecting to see 19. I know what a typical T bag here in this scenario is at a minimum 104 and at a maximum about 193. I can go into my blob area here and redefine exactly what a blob is. So if I were to move this to 105, we'll see that T bag disappear because it's actually smaller than I expect to see. So we can reduce that down to include that again. And again, maybe we don't want to pick up the external packaging of the T box as a blob at a given point, so I can increase this up to 250 to ignore out any kind of larger items that might actually be present that I don't want to ignore. So a nice little filtering option as far as being able to define exactly how many I want to see. So in our results section here, this is where I would set my pass-fail scenarios. So I want to find 19, and I always want to find 19. And you can see the inspection turns green, so now I'm doing exactly what I'm hoping to see here. We can hide this tool here as well. And maybe we want to start doing an inspection on area. So again, with the area tool, I mentioned before, is looking for an area based off of a surface area or or intensity information. So you can think this as almost like a pixel counter in a 2D space. So if I were to want to make sure that that open here is on a T bag, again, I can just reduce down. As you can kind of see as I grab and resize these objects, just grabbing an edge and pulling it down, really kind of utilizes exactly. It's a very ease of use product as far as being able to reposition a tool. So you don't really need to be a vision programmer in order to really utilize the vision software here. So again, this is looking for information based off of surface area, but I can use that intensity information now and say I want to find that open here. I can reduce this down to maybe look for just the darker pixels. And now as I scroll in here now, you can see, it might be better to move this one over to the, you can see here now that I am actually seeing that gray, or those darker pixels, and I get an area coverage of that open here in that grayscale kind of 2D pixel counter view. Now, if open here wasn't here, I would not get a coverage of the proper coverage that I'm looking for. So I could maybe go from 6 to 10% here. And we'll see that that passes. Now, if say the open wasn't there or the O wasn't there, the coverage is just not going to be enough coverage anymore. So, so that O really kind of being able to do that pixel counter in a 3D view, even though it's not 3D information I'm looking at, I'm utilizing intensity view. I'm still able to do 2D type inspections with 3D device, as well as being able to do inspections based off of 3D height information. So now if we go into a live view here, And now we actually have a scenario here where I actually failed it based off of 17 blobs. Even though the blobs are in there, they fall outside of my threshold of what I'm defining as a tea bag. So maybe the tea bag isn't formed properly or not filled enough to actually give enough volume. So that's why I'm getting a failure here, because I actually have two blobs that are smaller than my defined 95 millimeter square area threshold. Again, if I wanted to make sure that I find even the smallest of tea bags, you can always open that back up. And now I can find them all again here. So that's you know, obviously an inspection criteria. You know, if there is not enough tea in a bag, maybe it's giving you an output that's too small of a surface area or too small of an area, and I can define and fail something based off of an area, you know, an area being present. So now as I scan through these different images here, you can kind of see that I'm getting a count of information every single time to make sure that the presence of all those tea bags are present. Again, this might be a difficult 2D application, especially if there is a low contrast scenario. Obviously, you'd start seeing the background here too, so I'm actually ignoring out the bottom of the tea bag box because, again, reducing that amount of area that I'm actually doing an inspection on. Where a 2D view might have a tea bag, the background, which is dark as well. So this could be a very difficult application with a 2D view just for doing a simple content verification. We can kind of scan through a couple more of these images here as well. And again, nice thing about this is we do get a nice array of information that the blob tool is actually able to output. And in our results tab here, we can actually just go simply into that tool and output a number of blobs. And just in a customizable Ethernet output string, able to give you exactly how many tea bags I'm counting, and outputting that either over Ethernet IP, TCP IP, or Profinet. So able to have many different protocols as far as being able to transmit that information. Jump back into this here quick. So again, going into this, as we kind of touched on here, traditional 2D view might be very difficult to inspect this application. 3D obviously gives that height information, able to actually eliminate background information, where a 2D camera would be taking in the whole region of interest here, where 3D is actually able to just take the height information that I'm actually looking to inspect and do a count based on heights instead of based on contrast. Again, and not only, again, as we're not really just relying strictly on 3D information, but we also get that intensity information. So making sure that there is the proper text there where I'm expecting to see text. So doing a simple 2D pixel counter in essence with that area coverage tool with utilizing the intensity information. So able to multitask again, you know, with 3D vision, doing counts, doing presence verification, doing area calculations, being able to do 2D inspections based on text. So able to really multitask with a couple of different technologies, or a couple of different views, I guess, in a 3D view. Again, and there's some of the tools, again, that we kind of covered with our blob tool, you know, edge tools. Maybe I want to do a dimension of the T box itself at the same time, making sure that the package is actually the correct dimensions and the length and width. Maybe you look for a peak information here as well. Is one of these tea bags, you know, seated properly, or is it seated too high up? And a flap isn't able to close, so able to do inspections based off a peak. And then as well as being able to do that distance measurements and angle measurements. Maybe I want to determine the angle of the plane of the tea bag as well, and be able to do a pass-fail based on the orientation or position of a tea bag inside the box as well. And again, here's that simple blob tool doing that count based on that height information. And otherwise, that's my brief overview that I have as far as the technology, as far as the tri-spector goes and 3D triangulation. Some of the benefits that 3D information can give you over a traditional 2D sensor or 2D area camera. Being able to get that height information, be able to still get intensity information out as well, and be able to do a lot of multitasking scenarios where a traditional 2D view might struggle as far as especially low contrast scenarios or lighting issues that might come into play in the different ambient conditions in a setup. All right, I guess we'll open up to questions here now. If you guys have any questions out there, wherever everybody is, and I'm more than happy to address them as best I can.
Thank you so much, Ryan. Yes, if you have any questions, please type them into the chat section on the right-hand side of your screen, and we'll get through as many as time allows. But Ryan, some questions that came in, and I will ask them to you now. The first one is, if each blob had a unique identifying number printed on the top instead of open, like you demonstrated, could the system log the presence of each unique identifier and note the absence of one if it is expected?
Yes. So yeah, I can show you that quickly in the software here. So again, that blob tool outputs an array of information. So each of those blob indexes, I can get exactly the X, Y, and Z information of each one of those, with blob 0, in this case, being the blob with the biggest area. So I can actually resort those blobs as well, going to my advanced menu. So I can sort the blobs by, say, I want to sort them by Y in the descending. So now I get the blob index is being sorted by my Y value. I can output all this X, Y, and Z and area information, in my output string. So if I want to have a unique identifier, I can say, hey, blob index 2 should have a Y value of a range of 45 to 55, and then I can fail it based on, I know exactly which index blob is missing because I know a Y information. So yes, I can output all this array of information and sort based on position. I could sort based on area, or I could sort based on volume if I were doing a volume calculation as well.
Awesome. And the next question is, what is the maximum number, or what's the maximum speed that I can pass this package under the camera to have reliable data for inspection?
So the maximum speed is very relevant to the camera itself and what resolution you're actually utilizing. So I have a profile distance. Again, that profile distance is your how often am I taking a slice of bread or a scan. So I have, in this scenario, I'm doing a scan to 3.25. This is the 1008 unit, so our higher resolution version. So this will be a little slower than, say, our 1060 unit that has a bigger field of view but less resolution. Typically, from applications I've seen, depending on the profile distance, if I want to have a 1 millimeter profile, it's going to be a little less resolute, but I can get more speed out of it. The tri-spector itself scans at 2,000 scans a second, so 2,000 hertz. And then the size of the field of view actually comes into play. So the bigger the field of view, the less speed I'm going to get as well. We have done some logistics applications where, looking for dimension of boxes or looking for content of boxes going up to 2 meters a second. I have also done some bottling applications, again, as I mentioned, looking for the bottle cap or the tilt of the cap and running those at 600 or 650 bottles a second, or bottles a minute, to be able to detect reliably the cap presence. So it really depends on how much resolution you're really looking for to get your speed. Obviously, the more resolution, you're going to have a little less speed. But if you have a window where you're able to reduce resolution a little bit, you can definitely get a lot more speed out of it. But I'd say typically, meter per second and less is pretty standard. Half meter a second, you'll definitely get reliable data, as well as being able to get, about a half meter of speed or so.
Awesome. And is it also possible if the two tea bags are next to each other without a gap?
Yeah, there is. There are some filtering tools available in here as well. I might not get in a reliable area at that point anymore, but there are some erosion capabilities in the software as well. So I can, if I did have some tea bags touching, I can start to erode. And what the erosion does, it actually kind of starts eroding the outer pixels around there to start hopefully creating some separation. So you are able to start eroding out your blobs if you do have objects that are touching, and that can hopefully help create some of that separation. Vice versa, if you do have two blobs touching, obviously that area of those two blobs would be, say, instead of 190, all of a sudden I see a blob that's 360, I know that, hey, there's either two blobs touching right there, or I'm going to fail it because, there's, too much area there. So there are a couple different filtering options as far as being able to determine that. So there are condition-based in here. So if I do have two blobs touching, I can say if, a blob area is greater than 300, assume that to be 2. So there are some, different conditions that you can do inside the software itself to be able to overcome some of those touching blobs, but really filtering based off of defining the area as well as the erosion function, and then with the addition of conditions being able to kind of create your own condition if you aren't able to create that separation.
Great. Are these measurements data able to be output or export? Can you export any of these measurement
yes,
data?
Absolutely. Yep. So in the Ethernet result string is very customizable. So each one of the tools I add has information that I can get out of it. So that first blob, so I can get all that XYZ information. I can do, if I did have a distance measurement from an edge to edge, if I had a distance tool in here, that distance tool would also populate, and I can output a distance measurement as well. I can output a bounding box, the length and width of each one of those blobs as well. I can give the Z height information. So as you add more and more tools, you get more and more information that you customizably add into your Ethernet output string. So yes, you can get all that information out there. And we do have function blocks available in for Profinet. We do have an EDS file for Ethernet IP to really parse out that information, but it's very highly customizable as far as what information you actually want to get out of the devices.
Great. I have one more question for you before we're out of time. But what are a couple of benefits of using 3D vision over 2D?
What are a couple of the benefits over 3D over 2D?
Yeah, exactly.
Okay. Obviously, with 3D, again, we get that height information. So, again, since I'm utilizing the internal laser line as its internal light source, all the external lights that might be in a factory setting are not going to contribute to that image acquisition. A traditional 2D view, if the lights are on or lights are off, or there's a skylight, positioned nearby, and maybe it works great at noon, but it starts to not work as well at 5 p.m. just because the lighting's changing throughout the day. 3D won't have that issue. So lighting and ambient conditions really kind of become mute in a 3D case because I'm just using that laser line as its light source. So lights on, lights off, pointing a flashlight at it, you're going to get the same image every single time. Again, so lighting, low contrast. Low contrast is another scenario. Again, if I'm looking for, again, brown chocolates in a brown packaging, 2D view is really going to struggle because there might be very low contrast where I'm not able to find those edges in a 2D grayscale space. 3D, since it's utilizing height information, really kind of shines in those applications because I can actually determine presence or absence just based on the raw height information instead of utilizing or relying upon contrast information. So those would probably be the biggest ones, is low contrast, a little higher resolution potential as well with 3D, and as well as any kind of ambient conditions that might come into play. 3D also allows you to be able to ignore data, where 2D would see the whole background here as well. So it really kind of, you're able to ignore out data a lot easier with 3D as well.
Awesome. That's all we have time for today, but thank you so much, Ryan, and we hope to see our listeners again soon. We have a few more webinars happening before the end of the year, so please check our website for more information. But thanks again, Ryan, and have a good day, everyone.
All right. Thank you very much. Have a good day, everyone.